Hello, this is our second lesson for today, so be sure you did the solving equations with variables on both sides of the equal sign before you do this lesson. And we've been working so far with equations that have just one solution, and it turns out there are equations that have different solutions other than just one. So if you notice, if you look at the head of the columns, we have one solution, which is what we've been working with, no solution, and infinite solutions. So you may have also noticed that each one of these have variables on both sides of the equal. So we can actually identify whether an equation has one solution, no solution, or infinite, which means every number will solve it, before we solve by identifying the characteristics of each type of equation. So let's see if we can identify similarities in the following groups of equations. Let's start with an equation that has one solution. That's what we've been working with recently. So just like we did in our last lesson, we're going to start by eliminating one of the terms with a variable. So I'm going to start on the right side by taking away the two x's, which I then have to do on the other side. That eliminates, leaving negative 5. Don't forget that sign in front of the number. And 5x minus 2x is 3x minus 23. Then we continue solving by eliminating the constant on the side with the variable. And we have 3x equals negative 18. And our final step is to divide by 3. And x equals negative 6. By the way, if you need to pause at any time, please do. Okay, go ahead and pause if you need to copy this down. So we have one solution, and that solution is negative 6. So now let's see what happens. These equations look kind of similar, but let's see what happens when we try this type of equation. That looks very similar, but it says it has no solution. So we're going to start, and we always want to, I'm going to encourage you to always get rid of one of the terms with a variable on one side. So I personally like to start on the right side. So I'm going to take away 8 of the x's, and I have to do it over here. So on the side that I started with, it eliminates it, leaving negative 2. And on this side, it also has 8 x's. And if I take away 8 x's here, I also don't have any x's, a term with an x, but I do have a positive 7. And now I'm left with 7 equals negative 2. Is that a true statement? In fact, my variable has disappeared, so I do not have a reason to continue to solve. So in this situation, and this is why one of the reasons I encourage you to start with the variables, to get rid of them, I don't have a solution because my variable that I'm trying to find out what the value is has disappeared, and I'm left with a statement that's not true. So when you have a situation where you have two numbers and they do not equal each other, then this is a situation where there's no solution. So we're going to write exactly that. There's no solution. There's no value for x that we can substitute in that's ever going to make this equation true. And that's because if I took, so for instance, 8 times 2 and I'd added 7 to it, it would be different than 8 times 2 minus 2. So there's no way we can ever find a value that will make, value of x that will make this equation true. So our next situation says infinite. And that means, and they sometimes say infinitely many. It means any number will solve this. So let's see what happens when we try to solve this. We're going to go ahead, drop our wall, and I'm going to go after my terms on the right side. So there's 3 x's, so I'm going to take away those 3 x's. And I'm going to do exactly the same thing on the other side. Well, these eliminate, leaving a positive 7. And since this is identical on this side, this also eliminates, leaving positive 7. And 7 equals 7 is absolutely true. 7 does equal 7. You may have already noticed when we started this, these are exactly the same. So if I put 3 times 2, if I substitute 2 for x, and add 7 to it, it's going to be exactly the same thing as 3 times 2 plus 7 on this side. So this is considered a situation where we have infinite solutions. And again, sometimes it might be written as infinitely many, meaning every single number will make this true. I just happen to pick 2, but we could also use 4. We could use -5. If I put any number in for the x's, since both sides are identical, then both sides would remain equal. So now let's try this one more time. Let's go back to the column that has in our one solution column. So we're going to start this, once again solving, and we're going to start solving by eliminating one of the terms with a variable. So we're going to take away 5x. And the purpose is to eliminate one group of variables that have an x in it, and I have -10 left over. Always remember to take the sign with it. If I have 9x and I take away 5 of them, I have 4x, and my constant of +6 is left over. As we continue to solve, we're going to subtract 6 on both sides, and that leaves 4x, so we eliminate our constant on the left side, and we have -16. And our final step would be to divide by 4, and so x equals -4. -4 is the only solution that will make this true. So for instance, to prove it, if I took -4 and substituted it in the original equation for x, 9 times -4 is -36, and if I add 6 to that, I'm going to get back -30 if I use -4, which is the solution. On the other side, if I take 5 times -4, if I substitute -4 where the x is, that would be -20. -20 minus 10 would also give me -30. And so both sides would be equal. However, this is the only number that I could substitute for x that would make both sides remain equal. So that's the one and only solution. So now let's go to the column that says that there's no solution. So we're going to start by dropping our wall down. I'm going to start on the right side, and I'm going to add 5x this time because I see -5x. But I also see -5x on the left side, which means that both of these terms are going to eliminate, leaving me with a constant of +6 on this side and a constant of -10 on this side. That is not true. 6 does not equal -10. And to continue solving, I need to see my variable x, which I don't. And so this means that there is no solution. This is not true. And if we use our logic, if these two terms are identical, and then on this side I add 6 to that, and on this side I subtract 10, I'd never be able to keep both sides being equal. So finally, let's look at the last column again. If we start solving, we would eliminate one of the terms with the x. And I just noticed a typo. On the right side, this should have an x with the 6. So that was my typo. Would you please fix that? So I would take away that terms with 6x, and I would once again eliminate the term with the x's on both sides. And this time I have a -8 as a constant and -8 as a constant on the right side as well. And that's a true statement. -8 does equal -8. So this means that any number can be substituted for x and both sides will remain equal. And so they sometimes refer to that as infinitely many solutions. And that means any number will answer that. So you may have noticed too in the first example, both sides look identical. In this example, they just moved terms around. They both had a positive 6x term with 6x, and they both had a -8 on both sides. So they both of the constant and the coefficient were identical. Therefore, we ended up with any number being able to solve that. So let's start in this column. The characteristics, as I just mentioned, for our equations that have infinitely many solutions is that I'm going to end up seeing that the coefficient of the variable, in this case we're using x, the coefficient, the number with the variable, is the same on both sides of the equation. And it also turns out the constants are the same on both sides. The constants are numbers without the variable. The constants are the same as well. So let's go over to the column that mentions, or that says that there's no solution. So in both of the equations we looked at, the coefficients that were in front of the variable, in this case it's x, are the same. So the coefficients are the same. That happened for both example equations. Coefficients are the same. And if I look at the constants, the numbers without the variables, the constants are different. All right, and finally, the characteristics of the equations that we use to get one solution. Well, if I look at these, both of the coefficients of the variable were different. So the coefficients of the variable, the number in front of the variable, are different. And if I compare that, this is the only one that has coefficients that are different. Both the no solution and infinite solution had the same coefficients. And then for the constants may or may not be the same. So the constant may be the same or different. In this case, they were different too, in both of the cases we used. They may be the same or they may be different. Okay, so how are we going to use this? Let's look at the next page. We can refer back to the first side at any time in order to help us. This says, see if you can use the characteristics, what we noticed about the coefficients and the constants, what we've listed for each type of solution, one solution, no solution, infinite solutions, without actually solving the equations below. So we're going to try to just look at the characteristics without having to solve. If I look at them and notice the specific characteristics, we're going to be able to tell whether there's one solution, no solution, or infinite solution. And this is called upon inspection. It means just by looking at it, okay? Which means that we're just looking and analyzing the characteristics of the constant and coefficients. So we're going to be able to identify each equation as having one solution, no solution, or infinite solutions without solving it. And this is what it looks like. I'm going to start with the term that has x in it. Are they the same or are they different? Well, they're different. And if I look back now at the characteristics, the only one that says the coefficients are different is one solution. The other two have the coefficients being the same. So now I automatically know, without going further, that because the coefficients are different, equation number 1 has one solution. So I'm going to write that equation number 1 has one solution. So let's try one more together, and then I'd like you to try and confer with a partner. When I look at the second equation, I see that I'm going to start with the coefficients. I have negative 3a and negative 3a. The coefficients of the variable are the same. So if I look at back at your first page, I notice that in order to have one solution, the coefficients have to be different. So this will not have one solution, but it could have no solution or infinite solutions because in both of them, the coefficients are the same. So let's inspect or look back at that equation again. So the coefficients were the same, but the constants are different. This one has positive 8, this one has negative 6. So let's refer back again to our first page and see what they say about the constants. Well, in order for it to have one solution, the constants are different, and that's what we have. If it's infinite solutions, the constants would be the same. So this must mean that the equation number 2 meets both of these characteristics. Our coefficients are the same, and our constants are different. Therefore, this has no solution. So we're going to write that in the no solution column. Now, I don't want you to think that the reason number 1 went in the first column and number 2 went in the second column, that just happened. So you're going to go ahead and try looking at the coefficients and the constants for each one of these and decide whether they have one solution, no solution, and infinite solutions. And I'd encourage you sharing out with a partner. So thank you for being patient in this long lesson, and I hope that you have a wonderful afternoon. Take care.